A very good evening to everyone, and thank you all for joining this 2 week, that is 1 week online from 31st October to 5 November, that is the online mode, and in the second week it will be offline, that from 7 to 11 November. This ATAL FDP that is approved by the AICT. So now here Professor Seema Saini is the coordinator and I am Dr. Anju Saini who is the co-coordinator of this FDP from Mathematics Department, Graphic Era deemed to be University. I feel privileged to welcome you all today on behalf of Department of Mathematics, Graphic Era deemed to be University to the 2 week ATAL FDP on mathematical modeling of differentially rotating stars in stellar system. I welcome our speaker and the participants from different walks of life. You have come here to share their knowledge and vast experience with the researcher community. So we hope this 2 week ATAL FDP would help research expand their mental horizon in the field of science. Anyway, I can't express our gratitude enough. These 2 weeks are going to be all about you because without you, there had been no meaning of this FTP. So always remember this point. Now we are very thankful to our chief patron, Professor Kamal Ghanshala, who is the president of Graphic Era deemed to be University, and our patrons, Professor R.C. Joshi, Chancellor of Graphic Era University, and Professor Sanjay Jasola, Vice Chancellor of Graphic Era deemed to be University, to organize this ATAL FDP. Now I want to tell you more about this FDP. As you know that it is 2 week FDP. So in 1 week, that is the online mode FDP from 31st October to 5 November, there is daily one lecture from different speakers. That is 7 to 9:30 p.m. And you have to listen carefully and make summary about all the lectures, all participants. And it is the part of your ATAL FDP. And you can email that is summary to email us with your name and the affiliation. After that second week, that is the offline mode of this FDP, that will be 7 to 11 November. In offline mode, you will get some lectures, some lab practices, and first day is the offline mode. You have one visit, that is a lab visit. So we will do this visit in our DRDO lab in Dehradun. Some more activities will also be there. So we will make 5 to 10 participants groups. In each group, we take the 5 or 10 participants to complete their tasks. In this FDP, you will be eligible to get certificate if you have 80% attendance and 70, you get the 70% marks which I give you the test. So you have to give at last the one test in which you have to secure 70% marks. Then you will be eligible to get the certificate of this 15 days FTP. And we will also distribute some books on programming to our best 20 participants. And who will get who will have the above 90% attendance, they will get an excellent certificate also from the AICT. So now, without further delay, we start our uh, session talk, which will be given by Dr. Mohammed Tamsir. So that is the Mohammed Tamsir is currently working as an assistant professor in the Department of Mathematics, Jazan University, Jazan, Saudi Arabia. He has more than 8 years of teaching and research experience. He has published more than 60 research papers in international peer-reviewed journals. His research field are numerical analysis and partial differential equations. He has worked as a reviewer in many international peer-reviewed journals. So now I welcome to our eminent speaker, And that gives here one talk that on reconstruction of a potential coefficient in the Rayleigh-Love equation with non-classical boundary conditions. So please, see, sir.
Thank you, ma'am. Good evening, all of participants. My PPT is visible?
Yes, sir.
Okay. So I will discuss for the reconstruction of a potential coefficient in the Rayleigh-Love equation with non-classical boundary conditions. So okay. So here we reconstruct the potential term in the fourth order Rayleigh-Love equation from the additional measurement. Actually, this inverse identification problem is ill-posed problem because by being sensitive to the noise. However, it has a unique solution. Since the noisy data is introduced, the investigation and analysis model real circumstances where the practical quantities are naturally infested with the noise. This lecture is divided in two parts. In the part 1, we will discuss the discretization of the direct problem by using collocation method based on the spline basis function. In the part 2, we will discuss the inverse identification problem where Tikhonov regularization technique is used to find the stable solution. However, the main focus will be on the part 1. So, first of all, the problem formulation. So here we consider Rayleigh-Love equation del square u over del t square minus del power 4 u over del t square del x square minus del square u over del x square equal to a of t u plus f. Here a of t is a potential term and f is a distributed transverse force. And this we will consider with the initial condition ux comma 0 equal to phi, ut x comma 0 equal to psi, and boundary and non-classical boundary conditions are u0 comma t equal to 0 and ux1 comma t plus d uxx1 comma t equal to 0. And the additional measurement is ux naught t is equal to h of t. And the compatible conditions here phi 0 equal to phi double dash at the 0 equal to the value will be 0. Phi dash 1 plus d of phi double dash 1 equal to also 0 and psi of 0 equal to phi double dash 0 equal to 0. Psi dash plus d phi double dash 1 equal to also 0. h0 must be equal to phi x naught and as derivative of h will be equal to psi x of naught and f0t equal to f double dash second derivative of f at 0 comma t equal to 0 and fx 1 comma t plus d fxx 1 comma t equal to 0. And this is the theorem for the uniqueness, and this already proved by the authors of the reference theory. And if these all conditions will satisfy, then the solution will be the unique. Solution will exist and will be the unique. So now I'm coming to the discretization procedure. So here we apply cubic B-spline collocation technique because this problem is second order in the space. So here we have chosen cubic B-spline basis function. First, we have need to divide the domain, problem domain 0 to 1 into the mesh of equal length, which is delta x equal to h equal to 1 over m. And for the discrete form, we have taken u x comma t means at xi comma t is equal to u ij, and a of t is equal to a of j, and h xi comma t is equal to hi j. So throughout the problem, we will use these notations. And here we have used chosen this cubic B-spline 1 over h power 3. X minus xi minus 2 power 3. This is when the interval is xi minus 2. This is from closed from the one side, and xi minus 1. This is open from the another side. X minus xi minus 2 power 3 minus 4 x minus xi minus 1 power 3. This is at the interval xi minus 1 xi. and xi plus 2 minus x power 3 minus 4 xi plus 1 minus x power 3. This is on the interval xi comma xi plus 1, and xi plus 2 minus x power 3 when the interval is xi plus 1 and xi plus 2. Elsewhere the value will be 0. So here this solution, approximate solution ux comma t, this we can express as a linear combination of the cubic B-spline basis functions and time dependent quantities as this ux comma t equal to summation k equal to -1 to n plus 1 tk of t into bk of x. Here ck is a time dependent quantity which we have to estimate by using the initial condition, boundary values of the initial conditions, and the collocation method. And bk are the B-spline basis functions. So since the B-spline basis function and its four derivatives vanish outside the region xi minus 2 xi plus 2, since each cubic B-spline covers 4 elements, so each element is covered by the 4 cubic B-spline functions. So spline, 4 spline functions covered by the interval xi plus 1. So the variation of u comma x comma t over the element can be expressed by the following formula: ux comma t is equal to summation I minus 1 to I plus 1 tk of t into bk of t. So here time dependent quantities tk we have to estimate, and bk we will use from the equation number 7. So here first we will use we will use the values of the B-spline. So at the point uij is equal to, so this k equal to I minus 1, ci minus 1, bi minus 1. So here bi minus 1 we will calculate from the equation 7. So this is at the interval I minus 1. So I minus 1 in this second one we will take x belongs to xi minus 1 because flows from this side, comma xi. So here we will use x equal to xi minus 1. So here xi minus 1 minus xi minus 2 power 3. This is h power 3 minus 4. Here xi minus 1 minus xi minus 1 will be 0. So h power 3 and outside is 1 over h power 3. So this value will be equal to 1. So here the coefficient of ci minus 1 j is 1. Similarly, now the second term here ci bi. So bi, now this is in the interval xi comma xi plus 1 in the equation number 7. So here using this xi plus 2 minus xi, this is 2h power 3 minus 4 xi plus 1 minus h minus xi, this is h power 3, and this value we will get 4. So here we are using this coefficient of ci is 4, and similarly next term is, third term is ci plus 1 bi plus 1. So here we will use the interval this xi plus 1 comma xi plus 2. So using this value xi plus 1, this h power 3 and outside 1 over h power 3 cancel. So this value is equal to 1. So here we are getting uij, approximated value of u at the node xi comma j is equal to ci minus 1j plus 4 cij plus ci plus 1j. Now we will find the derivatives of ux and uxx. So in the derivative, differentiate this equation number 9, and then again express this ci minus 1 b dash plus ci b dash I plus ci plus 1 b dash I plus 1. So for finding the value of b dash, we will use again equation number 7. First we will differentiate this equation, and again we will use in the same manner, and then we will get the values this 3 over delta x, means the first value is minus 3 over delta x, and the coefficient of ci will be 0, and the third value is 3 over delta x. Now for the second derivative, again differentiate this second time, and then use from the equation number 7 after differentiating again, and we will get the values this 6 over delta x square ci minus 1j minus second coefficient we will get minus 12 over delta x square cij plus third value we will get 6 over delta x square ci plus 1j. So now we will use these approximated values in the problem. So for discretizing the problem, this time derivative we have used this discretizes by using the finite difference method. So this del square u over del t square. First term is del square u over del t square. In the problem, del square u over del t square minus del square u over del t square del x square minus del square u over del x square. So time term we will discretize by using the finite difference method, while in the spatial derivative we will use this approximated values by the collocation method. So here this second order derivative we have discretizes by using the time derivative, and this del square u over del t square del x square. So u x x I j plus 1. Here also we have used finite difference, and spatial derivative we have written at the same u x x I j plus 1 u x x I j, and here in the u x del square u over del x square, here we have taken the average of this, means we are using Rayleigh constant here, and here also in the term of u also we are taking the average of this, and average of the this function g. So now simplifying this equation, we will get this equation 1 minus delta t square over 2 aj plus 1 uij plus 1 plus minus 1 minus delta t square by 2 uxx ij plus 1 is equal to 2 plus delta t square by 2 aj uij plus delta t square by 2 minus 2 uxx ij minus ui at j minus 1 plus uxx I j minus 1 plus this delta square by 2 di j plus 1 plus dij, and I will run from 0 to m and 1 to m. So now here, because j minus 1, this is the time for the time when j equal to 0, this here we will get I minus 1. So here we will use the initial condition for j equal to 0. So using the initial condition, this equation number 14 will convert into this 2 minus delta t square by 2 a1, this ui1 plus minus 2 minus delta t square by 2 uxx I1 is equal to 2 plus delta t square by 2 a naught ui naught plus minus 2 plus delta t square by 2 uxx I naught plus 2 delta t psi xi minus psi double dash xi plus delta t square by 2 gi1 plus gi. This equation only for j equal to 0, and the equation number 14 for j equal to 1 to n. So now here we will use this notation minus 2 minus delta t square by 2 a1. This we will use a1 capital A1 bar minus 2 minus delta t square by 2 is equal to b naught bar. Similarly, this b naught bar and e bar. So this equation number 15 becomes to this a1 bar ui1 plus b naught bar uxx I1 is equal to d naught bar ui naught plus e bar uxx I naught plus 2 delta t psi xi minus psi double dash xi plus delta t square by 2 gi1 plus gi naught. So now here we will use the approximated values of u and uxx from the previous equations. So after using the values of approximated values of u and uxx and simplifying the terms, we will get this equation. A j plus 1, here j is 0. So this is a1 bar plus tau 2 b1 bar ti minus 1. Here we will use in these two equations, because this equation number 14, equation number 15. Equation number 14 for j equal to 1 to n, and equation number 15 only for j equal to 0. So first we will use in the equation number 14. So now we will get this a1 bar ui1 plus b naught bar uxx in this equation, and then we will use the equation number 15. So here, using the equation number 15, we will get this a1 bar plus tau 2 b naught bar ci minus 1 because j equal to 0. So plus for A1 bar minus 2 tau 2 V naught bar Ci1 plus A1 bar plus tau 2 V naught bar Ci plus 1 at 1 is equal to right hand side quantities at C naught. Ci minus 1 C naught, here Ci naught and Ci plus 1 naught. And this 2 delta yes, 2 delta T psi xi minus psi double dash xi plus delta T square by 2 Gi1 plus this is Gi, by mistake I have written H, Gi naught I equal to 1 to m minus 1. So similarly here we will use the approximated values in equation number 14. Then here we will get Aj plus 1 bar plus tau 2 B1 bar Ci minus 1 J plus 1 plus 4 Aj plus 1 bar minus 2 tau 2 B1 bar Cij plus 1 plus Aj bar plus tau 2 B1 bar Ci plus 1 J bar is equal to Dj bar plus tau 2 E bar Ci minus 1 J plus 4 Dj bar minus 2 tau 2 E bar Cij plus Dj bar plus tau 2 E bar Ci plus 1 J plus delta T square by 2 Gi plus 1 plus Gi. And so now here this you can see here Ci minus 1, Ci and Ci plus 1 and I from 0 to m. So if we use I equal to 0, then C minus 1, and when we will use I equal to m, then C m plus 1. These nodes will be the outside the problem domain. So first we need to remove these for finding the unique solution. So here we need to remove Ci minus 1 and Cm plus 1. And for this we will use the boundary conditions u0 comma t equal to 0 and ux 1 comma t plus d uxx 1 comma t equal to 0. So using the collocation in these two boundary conditions, we will get Ci minus 1j plus 4 C naught j plus C1j equal to 0. This is from the equation number 10. Yes, yes. Uij here we will use at the x equal to 0, means we will take I equal to 0. So this u naught t means u naught j is equal to C minus 1 j plus 4 C1 plus C 1 j. So here we will get this equation number 20. And similarly here in the first derivative ux and uxx, here we will use in the equation number 10, 11 and 12. We will use I equal to 0 and simplifying this equation, then we will get this minus tau 1 plus d tau 2 Cm minus 1j minus 2d tau 2 Cmj plus tau 1 plus d tau 2 Cm plus 1j equal to 0. Now from these two equations 20 and 21, we will get C minus 1 j equal to, from the first equation, minus 4 C naught j minus C1j, and from the second equation Cm plus 1 we can find from these two equations. So for I equal to 0 in this equation number 19, when I equal to 0 and I equal to m, then we will use these equations 22 and 23, and then we can find these equations. So in the equation number 20 from 19, using I equal to 0 and I equal to m, we will get these two equations. Minus 6 tau 2 b1 bar C naught j plus 1 is equal to this minus 6 tau 2 e bar C naught j minus 6 tau 2 C naught j minus 1 plus delta t square by 2 g naught I plus j plus 1 plus c naught j, and the second equation is 25. So these two equations I equal to 0, I equal to m, this equation number 24 and 25, and equation number 19 for I equal to 1 to m minus 1. So these we have m plus 1 equations. So these m plus 1 equations we can write as a linear system of equations. This is a time Cj plus 1 when j is 1 to n. So this is a tridiagonal system, and here the notations B1, C cap, Q cap, we have used these and the values of this written here. So after solving first here, because this j equal to 1 to n, and for j equal to 0, we have different equations. So j equal to 0 from the equation number this 17, this for j equal to 0. So here also ci minus 1 and ci plus 1. Here also when we will use I equal to 0 and I equal to m, then c minus 1 and cm plus 1, these nodes will be the outside the problem, outside the domain. So here also using, we'll use the boundary conditions here for I equal to 0 and I equal to m, using this this equation number 22 and 23 in 17. Then we will get these two equations, minus 6 tau 2 b node bar c node 1 is equal to minus 6 tau 2 e bar c node 0 plus 2 delta t psi x naught minus psi double dash psi xx x naught plus delta t square by 2 g naught 1 plus g naught 0. So and the second equation when we will use I equal to m, and after this we will get this a1 bar plus tau 2 b node bar 1 plus tau 1 minus d tau 2 over tau 1 plus d tau 2 cm minus 1 1 cm minus 1 1 plus 4 a1 bar minus 2 tau 2 b node bar plus 2 d tau 2 over tau 1 plus d tau 2 a1 bar plus tau 2 b node bar cm1 is equal to d node bar plus tau 2 e bar 1 plus tau 1 minus d tau 2 over tau 1 plus d tau 2 cm minus 1 naught plus 4 d naught bar minus 2 tau 2 e bar plus 2 d tau 2 over tau 1 plus d tau 2 d naught bar plus tau 2 e bar cm naught plus 2 delta t psi xm at minus psi double second psi xx at xm plus delta t square cm1 plus cm naught. So from here we can find this using the boundary conditions. We will get these two equations 27, 28 and equation number this 17. 17 for j equal to I equal to 1 to m minus 1 for j equal to 0, and equation number 24, sorry, is 27 and 28 for I equal to 0, j equal to 0, and 28 for I equal to m and j equal to 0. So again, these two equations, three equations, we can write as a linear system of equations at this system at j equal to 0, means at the time j equal to 0. So here the notations C naught, P cap, Q cap we have using we have written here in this slide. So here before starting the solution, because here we will find by using this equation system 29, we can calculate this C naught 1, C11, this vector at the time at 1. But here in the equation you can see 27, 28, 20, 25, 19 and 17. So here to the right hand side, C at the C naught, Ci minus 1 C naught, Ci naught, Ci plus 1 C naught. So before starting the solution of this system of linear equation, we need the values of C at 0, j equal to 0. So for that we will find this initial vector at time j equal to 0. So for finding this, we will use this initial conditions and boundary values of the initial conditions. So initial condition ux comma 0 equal to phi x at the time j equal to 0. So using the approximated value of u from the equation number 10, we will get ci minus 1 0 plus 4 ci 0 plus ci plus 1 naught is equal to 5 xi, and this equation gives m plus 1 equation, and because here ci minus 1 when I equal to 0, ci minus 1, and when I equal to m, cm plus 1. So here there will be m plus 3 unknown. So for the unique solution for this term, for this system, we need to wipe out c minus 1 and cm plus 1 from the this system. So for that we are using this derivative at the boundary, derivative of the initial condition at the boundary ux 0, 0 is equal to 5x naught. So using the approximated values of ux from the equation number 10, 11, and 12, this we will get c minus 1 naught is equal to c1 naught minus delta x over 5 x x naught. This is the value of c minus 1 at the time j equal to 0. And similarly, we will find this on the second boundary ux 1, 0. So in the second boundary, we will use I equal to m. Then we will get the value cm plus 1 the time j equal to 0 is equal to cm minus 1 0 plus delta x over 5 x xm. So using this value, these values from the equation number 31, 32, c minus 1 at time 0 and cm plus 1 at time 0 in the equation number 30, we will get this system. After solving this system, we will get the values of c, this time dependent quantity at the time j equal to 0, and after finding this value at the time j equal to 0, we can solve this system 29. Just from this system, we will get the values of c at the time j equal to 1. And after finding these two, solving these two systems, we can solve the system this 26. And these values we will get from j plus j equal to 1 to n, up to n. So here we will get the values of all time dependent quantities. So yeah. So using these values in the number 10, we will get the solution of this problem. Now we will discuss the stability analysis of this discretized problem. So for the stability, we have taken gx equal to 0, and we will suppose this potential term at is equal to b bar as a local constant. So after using these values, this equation, we will get a cap ui j plus 1 plus b cap uxxi j plus 1 is equal to p cap dj uij plus e cap uxxij, this plus minus, sorry, here minus ui j minus 1 plus uxxj, and where the values of a cap, b cap, d cap are defined here. So again here in the question number 33, using the values of u and uxx from the equation number 10 and 12, we will get this equation number 34. A cap plus tau 2 b cap ci minus 1 j plus 1 plus 4 a cap minus 2 tau 2 b cap ci j plus 1 plus a cap plus tau 2 b cap ci plus 1 j cap is equal to d cap plus tau 2 e cap ci minus 1 j plus 4 d cap minus 2 tau 2 e cap ci j plus d cap plus tau 2 e cap ci plus 1 j plus tau 2 minus 1 ci minus 1 j minus 1 plus minus 4 minus 2 tau 2 ci j minus 1 plus tau 2 minus 1 ci plus 1 j minus 1. Here now we will use this trial solution Cij equal to delta j ek I phi as a trial solution. where the value of k is equal to under root minus 1. So using this value, in equation number 34, we will get this 2a cap plus tau 2 b cap cosine phi plus 4a cap minus 2 tau 2 b square delta square minus 2 d cap plus tau 2 e cap cosine phi plus 4 delta d cap minus 2 tau 2 e cap delta and plus 2 1 minus tau 2 cosine phi plus 4 plus 2 tau 2 is equal to 0. And this equation can be written in this theta 1 delta square minus theta 2 delta plus theta 3 is equal to 0. And where the values of theta 1, theta 2 and theta 3 are this given below. So now because this is here delta square for the second derivative in the time, so here we will use the root Herbig criteria in this equation number 36 for getting the necessary and sufficient conditions for the stability of the described system. So here we will use this under the transformation delta is equal to 1 plus rho over 1 minus rho. So after using this delta in equation number 36, we will get this equation number 37 theta 1 plus theta 2 plus theta 3 rho square plus 2 theta 1 minus theta 2 rho plus theta 1 minus theta 2 plus theta 2 equal to 0. And for the stable solution, there these the coefficients of the rho square rho and this constant term, this must be greater than equal to 0. So now using the values of a cap, b cap, and d cap, e cap, and tau 2 in the equation and this here theta 1, theta 2, theta 3, and using this value, you will get this theta 1 plus theta 2 plus theta 3 is equal to 16 cosine square of 5 over 2 plus 8 plus 64 over delta square sine square 5 over 2. And this we can see this value wants to be will be greater than equal to 0 because here is cosine square, here sine square, and this coefficients are the positive. So this value will be greater than equal to 0. And the second condition theta 1 minus theta 2 is here after using the values we will get this 2 plus b delta t square 2 cosine square 5 over 2 plus 1 and this 24 over delta square 1 minus delta t square sine square 5 over 2. This value is also greater than equal to 0. And the theta 1 plus theta 2 plus theta 3 this is equal to we will get 24 delta t square over delta x square sine square 5 over 2 and this minus 2b delta square 2 cosine square theta 5 over 2 plus 1. So here because the coefficient of the sine square cosine square positive and this because delta t square over here delta x square in divide and the coefficient is large, so this value also will be greater than equal to 0. So here we the conditions for the stability, all three conditions are satisfying. So the this problem, this described system of this Rayleigh-Love equation is unconditionally stable. So now this inverse problem. In the inverse, we have used this Thikov regularization technique here. So by using this minimized function, fa is equal to this u x naught t minus ht norm L2 norm plus lambda A2 L2 norm. In this equation number 38 this u solves one equation number 1 to 4 for the unknown A when potential A is given. And lambda here, lambda is a regularization parameter. So for the discrete form, this equation number 38, we can write fa bar is equal to summation j equal to 1 to n and this u x naught j minus u h t square plus delta summation j equal to 1 to n a j square. So here we have used MATLAB subroutine, and this is given in the reference number 1. So we have to minimize this cost function. So RMS we have calculated by this formula, and here for the simplicity we have taken capital T is equal to 1, and the lower bound for AT we have fixed minus 10 raised to power 2. This is and the upper bound is 10 raised to power 2. So for the simulation, we swap HT in the equation number 39 with the perturbed data H E Tj. This is the noisy data. So here the noisy data is as epsilon Tj is equal to Hj plus epsilon j, and j is 0 to n, where epsilon j is the random variable with 0 mean and standard deviation sigma equal to p times maximum value of absolute value of Ht. So here p is the noise. So because this problem is a ill-posed problem, so if there will be if a small disturbance is there, then this will create a large problem in the solution. So we have need to stabilize the solution. And here we are using the B-spline basis function. So actually we have to use any polynomial in the collocation technique, but we have chosen the B-spline curve because B-spline curves have local support, meaning that the polynomial are positive only in the finite domain and zero elsewhere. And these spline curves have two advantages over the polynomial curve. For the large collection of the control points, a Bezier curve approximates the control polygon with a simple polynomial of the high degree. But the high degree polynomials take a long time to compute and numerically unstable, while the splines provide low degree approximations which are faster to compute and numerically more suitable. So, and any spline functions of the given degree can be expressed as a linear combination of the splines of that degree. So, this spline provides a simpler, numerically more stable approach. For these reasons, these splines have become extremely popular in the large-scale industrial applications. Because the collocation method based on these spline basis functions are better than the low order methods such as the finite difference method, because these spline based collocation methods provide solution at any point of the domain of the partial differential equation, while the large this finite difference means classical methods give results at the node points only. So here now we chose this example 1. So in the example 1, we have taken this input data phi x equal to u means this boundary u 0 comma t equal to phi x power 3 over 3 plus 3 sin phi x, and psi x equal to ut x comma 0 equal to 0, and x naught, capital X naught we have chosen 0.5, and the function ft we have chosen minus 1 over 3 2 plus 3t cosine t phi x power 3 plus 9 sin phi x, and the h means additional measurement we have taken 3 plus phi over 24 cosine t, and this input data will satisfy all the conditions of the theorem 1, means which gives the guarantee for the unique solution. And the solution we have considered here u x comma t is equal to 1 over 3 pi x power 3 plus 3 sin pi x cosine t, and at means potential we have taken 1 plus 3t. So this all data means input data from the equation number 43 to 46 will satisfy all conditions of the theorem 1 for the unique solution. So here now we are using this direct problem. First, we will solve the direct problem by using the collocation method. So we approximate this equation number 1 to 4 first. Equation number 1 to 4. Because equation number 5 has this additional measurement. Equation number 1 to 4 for the direct problem, and when we will find the inverse solution, then we will use this additional measurement, equation number 5. Yes. So we approximate the problem 1 to 4 first. This is the direct problem, and we have chosen this m and n 10, 20, 40, 80, and 160. So RMS are given in the table 1 for these values, not 10, 20, 40, 80, and 160. So we can see this 0.0121, this 5.4 e power minus 3, 2.5 e power minus 3, 1.2 e power minus 3, 6 into e power minus 4. And these are the plots for the exact numerical solutions and absolute errors for this A, B, C, D, and E. These figures we have plotted for the exact solution 45, approximate solution U by the collocation method, and we are finding the absolute error for the nodes 10, 20, 40, 80, and 160. So here we can see this absolute error for the node when m and n are 10, then this is 10 raised to power minus 2. So 3 into 10 raised to power minus 2. When the node is 20, 20, we are getting 1.5 into 10 raised to power 2. Then this 40, then we are getting 1 into 10 raised to power minus 2. When this 80, then 4 into 10 raised to power minus 3. And when the node is 160, 160, we are getting 2 into 10 raised to power minus 3. So as we are increasing the node, the absolute error is decreasing. So now here we will consider this for the inverse problem. This example 1. So now we will solve here inverse problem 1 to 5. 5 this additional measurement we will add or while solving the inverse problem. And we will use the input data this 42, this 42, 43. For minimizing the function, this is given in 38. So this 42, sorry, this 43, 44, and for minimizing this function is 39. So and initial guess, because when we will solve the inverse problem, this 80 is the potential term. When we will solve the direct problem, we have chosen the value of 80 is 1 plus 3t here, equation number 46. But when we will solve the inverse problem, we will remove this 80 and we will take the initial guess for A potential term. This is initial guess we have taken 1 for j equal to 1 to m. So here we will fix m and 40 for the inverse problem. Direct problem we are solving for the 5 nodes 10, 20, 40, 80, and 160. But for the inverse problem we have fixed 40, because if we choose 80 and 160, then this will take more time for the running the MATLAB program. Even for the 160, it can take 1 day or 2 days maybe. So we have chosen 40 and initiate the observation for this achieving AT means potential term. And first of all, we have taken t equal to 0. T is the noise. So first of all, we will solve without any noise in the measurement of 5. So the solutions are given in this figure 2, This left side figure A for the function minimize function 39. So here P0 is the noise 0. There is no disturbance in the problem, and delta lambda is 0 means regularization parameter is also 0, because regularization parameter we will use to stabilize the solution. And in the right hand side, this exact solution, numerical solution, and initial gas. So for the noise, P equal to 0 and lambda equal to 0. So this is the solution for without any noise and without any regularization parameter. So the function f is depicted in figure 2a, where the convergence is decreasing monotonically in the 20 iteration, and we have tolerance error we are getting 10 to the power -12 when solving this without any noise and without any regularization parameter in figure A, is left figure, and figure 2b, this is for the approximated AT with RMS. Here we are getting 3.7 into 10 to the power -2. So this figure shows a good agreement with the exact and approximated values. So now the second figure, now we will start to introduce the noise. Noise we have taken 0.01% and 0.1% to the ST. So in the equation number figure 3, we can see here this exact approximated potential, and left figure is with the exact solution with P equal to 0. Sorry, P equal to 0.01 and delta is lambda is 0. Means the exact solution with the noise 0.01 and regularization parameter 0. So here we can see disturbance in the solution when we are introducing a noise 0.01%. And in the second figure, we are using same noise 0.01%, and we are introducing a regularization parameter 10 raised to the power minus lambda and 10 raised to the power -7. So here we can see in the solution when lambda 10 raised to the power -7, solution approximate potential is more close to the exact solution. Means when we are increasing starting from the 10 raised to the power -8, then this there is stability in the solution in comparison of the first figure, and when we are going to the lambda equal to 10 raised to the power -7, solution is going to be more accurate, is more stabilized. So here, after using this approximated AT is depicted in figure 3 and 4. In the 4 also figure, this here we have taken the noise 0.1%. We have increased the noise from 0.01% to 0.1%. And this first figure is for the without any regularization parameter. So here a large disturbance in the solution you can see. And in the second figure, we are using the regularization lambda is equal to 10 raised to the power -7 and 10 raised to the power -6 and 10 raised to the power -5. We have taken 3 regularization parameters. So first we solving for 10 raised to the power -10 raised to the power -7 regularization parameter. So here the solution is stabilizing in comparison of the first figure, and when we are using lambda equal to 10 raised to the power -6, again more stabilizing, and when 10 raised to the power -5, this is more close to the exact solution. So here this figure 3 and 4a from A figure without any regularization. So when we are introducing the noise 0.01% and 0.1%, and we are not using the regularization parameter, then we can see the solution is unstable and oscillating with RMS value 5.0955 for the noise when noise is 0.01%, and the RMS value 37.65 when the noise is 0.1%, and when there is no regularization parameter. This is expected because the problem is imposed. So if we introduce the noise, there will be the oscillation in the solution, and the solution will be the unstable. So therefore, we have need regularization for getting the stability in the solution. So in the second figure B, I have shown you this. Second part in figure 3, figure 4, when we are introducing the regularization parameter, lambda 10 to the power minus 8 and 10 to the power minus 7 in the figure 3B, and lambda equal to 10 to the power minus 6, 10 to the power minus 5, and 10 to the power minus 7 also. There are 3 regularization parameters in the second figure. Number 4, 3, 10 to the power minus 7, 10 to the power minus 6, and 10 to the power minus 5. So when we are using these 3 regularization parameter for the noise 0.0%, 0.01%. So this will give the stable solution, and we are getting the RMS value 0.5619 and 0.3525, and the A is 1.16 and 0.9652 respectively. So from the figure 2B, 3 and 4, sorry, this 3 and 4, figure 2B, second part, this from the figure B2 and figure 3 and figure 4, when P decreases from 0.1% to 0.01% and then to 0, because in the first two we have taken no regularization, and this decrease noise they are taking here 0 and here 0.01%, 0.1% here. So this when P means the noise decreases from 0.1% to 0.01% and then to 0%, then the solutions evolve into a stable as well as more accurate solution. So how this we will choose this non-linear potential here in the second example. So this we can present after break. So can we take break? Can we take a 10-minute break? Hello?
Yes, sir.
Okay, ma'am. So we will
Yes,
start
sir.
after 10 minutes.
Yes, yes.
Thank you. Thank you, ma'am.
So now we have a 10-minute break. So after that, we will join again here. We will continue, but our talk will be started after 10 minutes.
Hello, ma'am. I think you stopped the recording. Hello.